Hello everyone, this is Rohit Maurya and this is the second lecture of Unit 5th of Slender, Sphere and Spring. So we already start the spring part, okay, and we did solve and analyze the closed coil Harris spring, which is one of a two part of a kind of spring, which is closed coil spring, specifically closed coil helical spring and open coil helical spring. So basically, the helical part stands for the sphericity of a rotating ring kind of a structure. Okay, so the first lecture containing the axial load when applied to the closed coil helical spring generates a deflection, and we did find the derivation of a deflection formula, and thereafter we drive the stress, how stress behave and generate in the closed coil helical spring under applying of a load W. So also we introduced the Wales constant in the last stress equation, where we did find that in the springs, where the springs containing the coil diameter and the diameter of a wire having the ratio is less than 1 or too much less than 1, then we don't have to consider it. And in case of where the coil of a spring variate gradually or radially, then in case we need to use the Wales constant in the form of spring index, okay, where spring index is find by the ratio of mean diameter of a coil to the diameter of a spring wire. So in this lecture we're going to find the behavior under axial torque which apply to the closed coil helical spring. So in this case, by applying the axial torque to the spring, what happens, how the reflection works, and what the analytical formula generate to analyze these kind of a spring. Okay, so if you find how this behaves, you just need to take any kind of a spring, just need to hold in your hand with and try to twist by placing one rigid and one is rotating to either side of the rotational slide or either side of the rotational axis. What happens, you see, when you do that, the number of coils, which is initially no matter how much they having the coil is, but if you are twisting in any direction of the rotating axis, okay, the number of coils changes. Either you closing the coils in the direction you rotate, or it opening the coils in the opposite direction. So when you apply a torque, there are two kinds of the thing happen. The change in number of coils exist. So by taking this particular concept in mind, we're going to solve in case of axial torque in the spring. Okay, so let's just get to the topic. Here it is. Okay, under axial torque, so let's assume that there is a T torque applied to the closed coil helical spring, and assuming there we have a small n number of counts at initial part when torque is not applied to the spring. Okay, and after applying of a torque, as you can see here, we are applying a torque, okay, in a diameter capital D. So in that case, if you apply torque, the number of rotation of a coil changes, either it's going to reduce or increase or changes, but it has to be changed, okay, in the case of applying torque. So if we assume initially the number of coils is small n, and after applying the torque the number of coils rest is n dash, but one thing is sure, the total length of a spring remains same. Either you close the coil by applying the torque or open a coil. Okay, so either side of the coil, the length of a spring remains same. Okay, so how can we solve that? So we start this equation with the bending stress equation. You already remember the bending stress equation, which is sigma upon y m upon I and E upon R. This is a bending stress equation. Okay, so in this equation we use these two parts. Okay, m upon I is equal to E upon R, where m is a bending moment, I is a moment of inertia, E is a Young's modulus, and R is a radius. So in this part we already know torque is a kind of a moment. Okay, because torque is equal to force into distance and moment is also force into distance, so torque is kind of a moment. Okay, so here m is equal to t, m is equal to t. Okay, bending moment applied to the spring is equal to torque. Okay, now upon E multiply here, so we have a EI. Now left part is capital R, because due to applying the torque in the spring, the radius of a coil changes. Either it going to be reduce, okay, or it going to be increase. So either side of the case, the ring has to be changed. So by applying this bending equation here, we have a formula T is equal to EI and 1 upon R is changing, okay, due to torque T or due to bending moment. But in this case we having a torque T in place of bending moment. So 1 upon R value becomes 1 upon R dash minus 1 upon R, because we know that by applying the torque T, the coil diameter has to be changed. Okay, so this is a 1 upon R, the changing part by applying, and this is the initial part. So by deducting these two gives us the basic equation of a torque and the coil of ring. So we already know that in either side of the case, the total length of a spring wire remains same, which is L is a spring wire length. So 2 pi n into R, where R is the initial coil radius, but in case of the radius changes, the number of coil is also be changed, but the total length remain the same. Okay, 2 pi n dash R dash. So these two value has to be same, because the length of the total wire by which the spring is made does not change. So we have this relation by equating these two, okay, which is n dash is equal to n multiply capital R upon R dash. Okay, now what? Now next part is, if phi is the angle of rotation of one end to the spring related to the other end about the axis. What this means? This is simply meaning this one part is fixed here and another end is going to be rotated due to torque T. So if we assume there is a twist of angle phi, okay, then how can we find the value of phi? How can we find the value of this twist generated due to torque T? Which easily find by this formula, 2 pi multiply increase in number of turns of the spring. So how much increase in the number of turns in the spring? By simply n dash minus n, where n is the initial number of springs and n dash is the final number of rings or coils in the spring after applying the torque T. So this much is increase number of turns in the spring by applying torque. So final formula becomes 2 pi n dash minus n, where by placing the n dash value here we have a formula 2 pi n r upon r dash minus n, and by solving it we have a value 2 pi n upon r, and this value 1 upon r dash minus 1 upon, some of you may not get to this form from this form, so let me just explain to you how this become this. So here we can easily take out n small n from these two components. Then what we left with, r upon r dash, okay, minus 1. If we take LCM, r minus r dash, we have r dash in this way. So by multiplying r inside and r in the denominator part, okay, so this form converted in this form, and we have a extra r value which is multiply here, and we already know that 2 pi n r is L, length of the spring wire, and this part 1 upon r dash minus 1 upon r can be find from this equation by dividing EI from T, okay, and by placing this value T upon EI here, so the formula becomes TL upon EI. This is a fundamental formula of change and angle of rotation due to torque T applying in a closed coil helical spring. Okay, so we have further modified this formula into different form by applying the value of moment of inertia and length L. So we have a further modification in the equation in the final form, where I is the moment of inertia of a wire cross sectional area, which is, you already know, I is equal to, for circular section is pi d to the power 4 pi d to the power 4 upon 64, and the value of L is, already we know that, 2 pi n upon r. So we can further solve this equation into this form. Okay, here we have a solution this, and then after we applied the value of length of the string in D form, pi dn, where d is equal to 2r. Okay, so we have a final equation 64 t dn upon e d power 4. Okay, and you also be find this relation by using the strain energy equation, which is this. We already know that strain energy equation is T square L upon 2EI, where T is a torque and rest of the part is same as usual notations. So strain energy is generated due to torsional effect is U is equal to half T tail T gamma angle of twist, we already used in the first lecture, and by placing this here we have a solution this, which is same as above. Okay, so this is a effect of axial torsion in the closed coil helical spring. Now let me just get to the simple question to discuss, to give you a way to solve in real life. So this is a question: a closed coil helical spring having 24 turns, means small n is equal to 24, made of an 8 mm diameter, which is a small d value. The mean diameter of a spring is 80 mm. Mean diameter of the spring is 80 mm, but this is a capital D. Okay, 80 mm is carried a load 250 Newton. This is the W. Determine the shear stress W and deflection and the stiffness of the spring. Take G is equal to this. So we give we have a W value of N, G, D, capital D. We already know the value of shear stress or torsional stress, which is 8 WD upon pi d power. We all placing all the value we can easily calculate the value of stress, which is 99.5 MPa, and we already have the formula of deflection, which is 8 WD power 3 N upon G dt power 4. Just placing the value and calculate the value, which is 71.4 mm. We know the stiffness of a spring, which is simply divide or take a ratio of a total load to the total deflection. Total load is 250 upon total deflection is, so this is the value. Means by applying 3.5 Newton of load, we have a unit deflection. Okay, this is a way to find the stiffness of a spring. So this is it. This is a chapter, or say lecture 2. In the next lecture we're going to solve for open coil helical spring. Okay, so use this lecture, make queries, question, ask anyhow you want, any way you want, just paste it to the comment box or contact me anyhow you want. Okay, so get ready for the next lecture. Thank you.